Problem 2024. You have a 2-meter long length of wire held in an east-west direction, which moves horizontally to the north. Wow. Alright, well, let's see. If I'm looking down at the Earth like I'm looking at a map, north would be toward the top of the page, east is to the right, west is to the left, and south is to the bottom of the page. So we have a 2-meter length of wire in the east-west direction, and it's moving north with a velocity of 15 meters per second. Alright, I think we have everything set up. Now, the vertical component of Earth's magnetic field, vertical in the room would mean somehow perpendicular to this page, directed downward. So B from the Earth is down. The way I've got the page drawn, it's this way. And they say 40 microtesla. They want to know what's the difference in potential between the two ends and which end of this thing, the west end or the east end, is positive. Alright, since this is a conductor moving through a magnetic field, the induced potential is E equals V L B sine theta, where this theta is the angle between the velocity and the magnetic field. So in our case, we've got 15 meters per second, a 2-meter length, 40 microtesla magnetic field, and while the velocity is north, the magnetic field is into the page, so that angle is 90, which gives an induced potential of 1.2 times 10 to the minus 3 volts, or 1.2 millivolts. Now, which end is positive? Now, there's no loop here, so we can't really apply Faraday's and Lenz's laws to get direction, but there are charges in this conductor moving through a magnetic field. So the direction of the force is given by V cross B. Alright, V is up, my fingers curl in, therefore my thumb points to the west. That's the direction of the force on positive charges, so I guess positives will accumulate down here, and negatives will accumulate down there, which means it's the west end that's positive.